Hello everyone, this is Zaida Kolami from ACMETSAF Research Company, and in today's video I'm going to talk about analysis of variance and especially about one-way ANOVA. So in this video we are going to talk about why we want to use ANOVA, what hypothesis do we make for running this test, what are the calculations, and how do we decide based on the ANOVA table, and how to run an example using Excel. So let's get to the next slide. Why do we use ANOVA and how can this test help us? So basically, the ANOVA studies the react of the variances to the factors. And as it turns out, from the name, it's all about variances and patterns of changing these variances due to the factors. So we want to know the effect of independent variables. We want to know the effect of independent variables on the dependent ones. Okay, so that's what we want to study. And then here when we say we are going to use one-way ANOVA, it means that we have just one factor, and that factor is categorized into multiple levels. So we have multiple categories of one factor. So in two ways or the other ones, you have more than one factor. Okay. So here, if we want to have an example to make it more clear for you, let's say we want to determine the impact of morning hours temperature on the time people wake up. So you want to see, does it make any changes on the hour people wake up when the temperature is minus, let's say, 6 centigrade degrees, or if it's plus 10 centigrade degrees. Okay, so then what we will do is that we categorize this factor into, let's say, 3 levels. So we want to study from minus 10, let's say, to 0, from 0 to plus 5, and from plus 5 to plus 10. And that's our 3 categories for one factor. So this is just one factor impacting the time people wake up. Okay, so let's say, what assumptions do we make for running an ANOVA test? So the first one is random selection. And what we mean by that is that we should gather samples randomly and independently. So they should not have any relationship to each other. There should not be any relationship between the data we get. So let's say we want to study the impact of medicine. So we have a medicine, and we want to study its impact on, let's say, on some people. Okay, we have, let's say, 3 categories of medicine, and we want to study the impacts on the people. These people, if these people are all, let's say, members of family, or there is any other relationship between them, your test is not true. Okay, so there should not be any relationship between the members of the sample selection. They should be gathered all randomly. So let's erase my beautiful handwriting. So the next thing is homogeneity, and it means that the variance within each plot which we want to test on is the same. So let's have an example here. Let's say we want to run a test on some employees of a company, and we want to test three programs of computer to see which one of them is the most influential on these employees' abilities. Okay, so we have, let's say, computer programs, and let's say there are three computer programs, 1, 2, and 3. And we want to study the impact that these computer programs have on the employees of the company. Now here, by homogeneity, we mean that these people should be randomly selected, and in all of these three categories. So we have people in category number 1, in 2, and 3. We should have like smart, less smart, or less intelligent, and all these things, all in the first category, the second category, and the third category. We cannot put all smart ones in here and take all less, IQ scored people in the second one and some other people on the third one. We should have homogeneity in all these selections. The third assumption that we make for this test is normal distribution of residuals. So the residual is the effects which are not described by ANOVA, and these should be distributed normally. So let's get to the next slide. Here, what we want to know is that what are the calculations? So here, the ANOVA is based on sum of squares. Okay, you can see the SS in here. This stands for sum of squares, and you can see the equation in here. So we have each x, and it's actually I. I'm sorry, it's I, it's not J. It's a mistake. So we have each data, and we want to subtract it from the average of all the data, and we do it for all these data from 1 to n, and then we sum up all of them. And I hope that it has some similarities in your mind to this formula, because this is actually this just has not this term in it, and this is almost the same, and that's why its name is analysis of variances. Okay, so it's almost the variance formula. So in here, in ANOVA test, all we're gonna do is to calculate the sum of squares for between groups, for within groups, and another one, which is the total sum of squares. Then we want an F statistic, and then we should have also degree of freedoms. So let's get to it a little bit. So as it turns out from the name, between groups, sum of squares, it means something like this. So let's say we have three sets of data. Okay, and we have data for each group. And then what we're gonna calculate for between group sum of squares is the variance between each groups. Okay, so between 1 and 2, between 2 and 3, and to the end. Okay, so the equation is something like this. SS between equals to J from 1 to the levels. So here we have 3 levels, and then we want to subtract each x from the total mean. Okay, and it's squared. I'm sorry, I dropped this one in here. We want to subtract the mean of each group from the total mean. It makes sense, okay? So we want to see how much the mean of each group is distributed from the total mean, okay? So, and then we multiply it by n of j, which is the number of individuals in each level. So if we want to have these calculations for this data set, all we're gonna do is to have the average for each level. So we make average of all these three groups. Then we want to subtract this average from the whole average. So we're gonna sum 1, 2, 3, 4, 5, all the numbers in level number 1, to all the numbers in level number 2, and all the numbers in level number 3. Then we are going to divided by all the numbers in here, and then we subtract them from each other and square it, and then we multiply by the number of individuals in each level, and then we sum it for all the levels. We do it for all the levels, and then that's it. That's the sum of squares for between groups. So, but what about the within groups sum of squares? So for within groups, like the equation is something like this. It's for within groups, and what we're gonna do is to then we're gonna have it for i's to the individuals. Okay, so we have to sum it up for individuals and all the levels. And then what we're gonna sum for is each x from the average of that level squared. So what it means is that, let's say again, we have three groups, okay? So that was, okay. So now what we're gonna do is that we have data all over here, okay? And also we have the average in here. We have the average of this one, and this one. What we're gonna do is to subtract each of these data from this average, and then we square it, and we do it for each individual for here. Then when we have this calculation done, we get to the next level. We do all the calculations, we subtract each number in here from the average in here, we square it and get to the third level, and we do the same. And that's the sum of squares within groups. So what we want is to do this variance for each level. So that's it. And then the total sum of squares is, of course, this one plus this between group from plus within group will be total sum of squares. And then we have an F statistic. So here there is another thing which is mean of squares. And the mean of squares is each of these one divided by degree of freedom. We get to all of these in the example we make in Excel, and I just explained them all in that ANOVA table, and don't panic here. And for the F statistic, we have these mean squares, and then we divide them by each other, and that's the F statistic. And the degree of freedom for each of them will be also explained in the example. So let's get to our example. So this is our Excel example, and the example I want to explain here is that we want to study the impact of higher elevations on the temperature. So this is not actually the one that I'm going to study right now. All studied already, and we know that by each kilometer higher that we get, the temperature falls like -5 or 6 or these things, um, and the temperature falls. Okay, so that's what studies show us. And here you can see I have three data set. These are my levels. Okay, so we know from before that so this is one factor, and that's temperature. Okay, so this one factor has three levels, which those three levels are 1 kilometer higher, and 2 kilometer higher, and 3 kilometers higher. We gathered data in all those higher elevations, and now we want to test this assumption that if these changes in elevations impact the temperature or not. So another thing that I forgot to tell you is the hypothesis we want to test using ANOVA. So by that I do not mean the assumptions, but I mean the null and alternative hypothesis. Okay, so I get to here, and So using ANOVA, we will have to test a null hypothesis which says all means of the groups are actually the same and these are all equal. But the alternative hypothesis tells us that these are not equal. So actually it doesn't tell us that specifically the group I does not equal to group J, but it just tells us that there are two groups that they do not have an equal mean. Okay, so that's what we want to test using ANOVA. So let's get back to the Excel file. So now what we're gonna do is to go ahead and go to data analysis. If you do not know how to add data analysis toolpack in here, you just need to go to files and options, and in add-ins, you will go for you will see analysis toolpack in here. I'm sorry, you will see analysis toolpack in here. You go for manage Excel add-ins, go and you will check analysis toolpack. Okay, so I have it already and I can see data analysis in analysis segment in data tab. Okay, so I click on that and you can see that the first option in here is ANOVA single factor, and ANOVA single factor exactly means one-way ANOVA. So I click on that. This window opens. Input range. My input range is this one. I have 29 data and I will select it with these labels, and then it asks me, it's grouped by columns of course, and check labels in first row. If you have them, check it because I will tell you why. And then it asks you the alpha. So here I am testing this hypothesis in 95% of confidence level, so my alpha is 5%. If you're testing in other confidence levels, you can change it in here. And the output range for me is here. I click OK, and you can see the output tables of Way Anova is now made for us, and we will hit to interpret them. So you can see ANOVA single factor right here, and then you have some summary. So this is the group's name. So the reason why I told you include these labels was that, okay? So my three groups are 1 kilometer higher, 2 kilometers, and 3 kilometers higher. Then there is the count of each group. So I have 29 data in each group, and that's obvious. Then there is the sum of all these data sets. So this is simply the sum of these data for me. Okay, so I go for AutoSum and you can see the exact same results with here. Okay, so that's just the normal sum. And then we have the average, and these are also the exact average of these three columns. Then we have the variance. These are also the variances of all these one. Okay, so for the first group, we calculate the variance separately, then for the second one, and for the third one. So that was just, as the name turns out, it's the simple summary of my data. The next table is the actual, useful table for interpret. So here you can see source of variation. So ANOVA's goal is actually to divide the sum of squares and the variances to different groups. Okay, so it wants us to see how are these variations coming from, where are they coming from. So it says between groups, as we told in the slides, and within groups, and the total sum of squares. So that's the simple sum of squares. You saw the equation in here. So it's the sum of squares for between groups, and then sum of squares for within groups, and of course the total, which is the sum of these two. Then we go for degree of freedom. So degree of freedom, so this is one of the things I wanted to explain in this part. So degree of freedom for between groups is the number of these groups minus 1. So we have 3 groups. Of course, 3 minus 1 is 2. So we have 2 degrees of freedom. Then degree of freedom for within groups, sum of squares is 29 minus 1 multiplied by 3. So you get the number of data within your groups, which for me is 29. Subtract 1 from it, it will get you 28. Then you multiply it by 3, which is the number of groups, and it comes 84. Then, of course, the total degree of freedom will be the sum of these two, which is 86. So the other term that you can see in here is the mean squares. So this mean of squares is a sum of squares divided by degree of freedom. Okay, so you can see if I divide sum of squares by degree of freedom, it will give me mean of squares, and I will also do it for the second one. And then you can see this f value in here. This f value or f statistic, or we can say maybe f statistic value, which you can see it right here, it is the result of dividing mean of squares together, dividing mean of squares of between groups to the within groups. You can see the numbers are exactly the same. And then here we have an important value, which is p-value. Okay, let's go to the whiteboard here. So a quick review for p-value would be that you know that we have something named p-value. Before that, we know that we can have some statistic tests, okay, like t-test, like z-test, or any other one. Or here we have f-test, okay? So when we have done these tests and we got the t statistic, z statistic, or f statistic, we get to those tests, sheets, which we can see, which we can read the p-value related to those tests. Okay, so right now here we have the p-value available. So then when we have the p-value, we get to compare p-value with we compare it to the alpha. Here we have worked under 95% of confidence level. So the alpha is 5%. Okay, so this is not D, this is alpha. Okay, so the alpha is 5%, and here we got to compare p-value to alpha. If p-value is less than alpha, then we will reject null hypothesis. And that means that we can accept the alternative hypothesis, and that means that somehow this test has significant meaning to accept the alternative hypothesis. Okay, so commonly the null hypothesis is that we cannot see any meaningful relationship, or we cannot see any meaningful difference or these things. So when we can accept the alternative hypothesis, it means that we are somehow the winner. Okay, so we can now accept the alternative hypothesis. If not, if p-value is bigger than alpha, we um we do not have enough evidence to reject null hypothesis, and we have to accept the null, or we should accept the null, or we should get back and maybe collect another independent values and run the ANOVA test again. Okay, so that was it. We get back to our Excel. Here you can see our p-value is so much less than alpha. So here we will accept and we will reject the null hypothesis, and we accept the alternative hypothesis, which was that alternative hypothesis is here, which was that the mean of these groups, the mean of two groups from these ones are not equal. So the other meaning is that really the changes in the elevation can impact the temperature. Okay, so that was for p-value, and here we have f critical value. F critical value is also compared to F statistic. So here we compared p-value to alpha. So let's get back to our whiteboard in here. Okay, so there are some notes for us. You compare p-value to alpha. Okay, then you compare F critical to F statistic. So I said if so I said if p-value is less than alpha, you will reject the null hypothesis. And here, if f critical is less than f statistic, or f statistic is the bigger one, then you also can reject the null hypothesis and accept the alternative one. Okay, so there was two ways to see how can you deal with your test. One of them is the p-value. If it's less than alpha, you can accept the alternative hypothesis. And also, if f critical is less than f statistic, you can also accept the alternative hypothesis and reject the null hypothesis. So that's it for today's video. I hope you learned something new. Please don't forget to give this video a thumbs up and subscribe to our channel. I will see you in the next video, and bye.